what are called current, voltage, resistance. They are the basic principles we'd like to talk about first. Now, I find the best way to describe these particular electrical properties, so these are electrical properties, is to actually describe them like if you had a water catchment system. All right? So imagine if you had a house here at this level and you had a tank there at that level, exactly the same level, let's say, that was as the house. All right? Now, if you fill up this tank with water, the highest part of the tank, if it's full, will determine how the water flows. So if the water is only at this level here, there's a tiny little bit of water at the bottom, then it's not going to flow in that direction, is it? It's just going to sit there. But if the tank is full, now we've got some what is called pressure, right, or potential for the water to flow. So if we had a tap here, so if we had a valve here of some kind, then the water would flow through that valve and into the home, but only so far as this pressure allowed. Does that make sense? Now, if we had a tank right up here, right, with a pipe going to this house, and we had a tap on this pipe here, right, how do you draw that? I think you draw that like that sometimes or whatever. And now you can see that the flow of the water through that pipe will be much faster, will it not? Because we have more pressure. And we have more pressure because the difference between this water level here, whatever that water level is, let's say it's there in the tank, that water level there and where the water is flowing to is quite large. You could call that, if this pipe isn't connected and nothing's flowing, you could call that a potential difference. Can you see that? It's only a potential of what might happen if you put in a pipe. Can you see that? And if you put in a pipe and connect the pipe and you left the valves of those pipes open, in other words, you allowed it to freely flow, the water will definitely flow from the highest location to the lowest location. Always. Now, if you put the tank down here, down the hill from the house, and you connected up a pipe, would any water in this flow up to the house? Of course not. Right? But if there was water in the house, it would flow back into the tank, would it not? Can you see that? So all of the pipes in the house would all empty and go back into the tank, if that was the case. You could say that that is a negative potential difference. So that one is a positive potential difference, and that one's a negative potential difference. Can you see that? Now, if you think of the water flowing is the current, and if you think of the potential difference, that is the voltage in electrical systems. So I'll describe these to you in a bit more detail. So you can think of the difference between where something is when it's in its normal state, and where it could be if we had some pressure or some kind of water attached to it, whether that's at a higher level. That's only a potential until we connect the pipe. Then we have flow. Once we have flow, you could say there is a current of flowing water flowing from the highest potential to the lowest potential. Does that make sense? And it's exactly the same principle in electronics, or electrical principle. We have to create a potential difference that causes electrons to flow, just like water would normally flow. Right? So we'll describe how we do that in a minute. Now, if I put a very big pipe in there, then the water would flow, and I opened the end of the pipe, the water would flow a lot faster, wouldn't it? Can you see that? But if I put a very, very thin pipe in there, like a little 4mm pipe that you use for that for watering systems, it doesn't matter how much potential was there, I would still limit how much flow would be able to be forced through that tiny little pipe. Can you see that? If I broke this tank altogether, in other words, I had no resistance at all of that water would instantly just flow down the hill, would it not? So that's like having no resistance at all. So can you see that the thickness of the pipe is like a resistance to the flow of the water? Does that make sense? The thickness of the pipe resists the flow of the water. And that is a very similar principle in electrical principles. We have resistors that resist the flow. They're like pipes that are thinner, and the higher the resistance, it's like the thinner the pipe. And the lower the resistance, the fatter the pipe, if you like. Mary?
So does that mean that if I have higher resistance, then my voltage will be lessened? No, my current. The voltage might be high.
The potential remains the same, but the amount of current that can flow through that resistance is obviously much lower. The higher the resistance, the lower the current. Does that make sense?
And I might be getting ahead of myself. Is there a relationship between the amount of voltage you have compared to the resistance?
Of course. The voltage, the current and the resistance are all related to each other.
So sometimes you can't have too high a voltage with this kind of resistance.
No, the voltage, remember, is something that is unchangeable to a degree in a system. In practical principles, you can draw current from something and lower its voltage. You know, in a battery car, how if you draw current from it and you keep drawing current from it and you keep drawing current from it, eventually the voltage starts lowering because it doesn't have the same storage capacity anymore. So in practical circumstances, the storage capacity of a potential difference in an electrical principle does have a sort of a lessening curve.
So it's like the tank.
It's like, well, it's similar to the tank in a way in that, like, when the tank is full, then obviously there is going to be more pressure than when the tank is empty.
Yeah.
Right? But the potential still remains the same. Does that make sense? It's just a potential of a possible flow. It's not actually the actual flow yet until water is present and you have a pipe that you can put it and make it flow through.
So the potential is something that always exists. It's
always exists.
Yes. But the battery is like the tank then.
The battery is like the tank.
Yeah.
Yes, yeah. And it doesn't have to be a battery. When we look through it, we'll find there's two types of current. There is what's called a direct current, which you hear the term DC. And most of you are used to, you know, getting a battery, picking up a battery from the store, and it's 1.5 volts DC. What that means is it's 1.5 volts, but it can only supply, so its potential difference between one end and the other end of its two pins is 1.5 volts. But it's can only flow in one direction, from the positive terminal to the negative terminal. And in practice, there's deeper issues than that, which we'll talk about later. But if you just think of it at the moment as from the positive terminal to the negative terminal, it can only flow in one direction, and so therefore the current is going to be direct current. It's going to be always flowing in that one direction. There are devices, which we'll talk about later, that you can swap the polarity of the voltage back and forward. In other words, it's like putting the tank up there and then grabbing the tank, running it down the hill and putting it down there, and then grabbing the tank, running it and putting it back up the hill again and going back and forward like that. In other words, the current will flow in that direction, and then it'll flow in the opposite direction once it's in the negative potential difference, and that's called alternating current, AC. You heard of that term? So AC, this alternating current, allows, and there are certain devices that are very easy devices to create, that create alternating current, and there are certain devices that can only create direct current. And you can convert between the two forms of current, which we'll talk about later as well. Nina?
The direct current, did I understand it right, that it goes from positive to negative?
Well, let's just assume that it does at this point in time. So, is that the best thing for me to say? Because the way electrons flow are from the negative to the positive, actually, but in terms of how we measure the current, it's from the positive to the negative. Does that make sense? So if you assume that it's from the positive to the negative, you'll see that there's and just remember that as a general rule, you won't go astray. But later on we'll learn that actually it's the electrons that provide the flow of current, and they are attracted to positive rather than attracted to the negative. They're repelled by the negative and attracted to the positive. Mary?
So when I have alternating current, does that actually double my potential difference? Is that like I'm just...
Well, there are a lot of... Yeah, we're running ahead of ourselves yet, but because we need to first do a few of the basic things first. But yes, the reality is that there are different properties of direct current in relation to properties of alternating current. And the reason why alternating current was actually invented was because of its properties. There are specific properties of alternating current that are very, very different to properties of direct current.
The potential differences, is that a constant or is that a concept?
It's a constant in the sense of when you have a certain amount of charge, and if you could think of the charge as how high the tank is in comparison to the house, in other words, you lift the tank up to 10 metres above the house, then let's call that 10 volts, right? And if you had it 20 metres above the house, now let's call that 20 volts, right? Does that make sense?
Yeah, so that's the potential difference.
That's a potential difference, and we call it a potential because it's not realised until there's a pipe. So it's only sitting there waiting, its energy stored, but not released. Does that make sense? Anto?
Is that static electricity?
Sorry?
Is that static electricity?
Yes, static electricity is energy stored, not yet released, but as soon as you touch something, you now provide a pipe. And zap, you get zapped, and that's the release of that potential that was already stored. Does that make sense? Exactly the same principle. Static electricity is a direct current generally, because you just do the thing on the carpet or whatever, you're storing up voltage, right, on your body, and it's not dissipating through the carpet because the carpet and your shoes are an insulator. As a result, the voltage builds up in your body to quite significant a level, and then you go and touch something that is grounded, that is at this level, and because of the potential difference between you and the place that would be grounded, as long as it can overcome the resistance, bang, you get a discharge, and you feel that zap of the current flowing all of a sudden through your body. Yeah? And you can feel it, can't you, in your body? It's a pretty strong feeling. Have any of you been electrocuted? A lot of you have been electrocuted. That doesn't bode well for the group. Yeah, I've been electrocuted too. So yeah. Most people who have worked with electricity at some point have been electrocuted. And what we want to do when we talk about safety is how we can circumvent that problem. The problem with what devices that we're going to produce is that potentially we can produce devices that are able to collect very high, large amounts of energy, right? That are very small devices but able to collect very high, large amounts of energy. That being the case, there is a high potential of us getting injured, right? And so we do need to understand what we need to do to stop injury. Does that make sense?
Does that mean when you say that energy, is that a high potential difference then?
Well, yes, there is a potential to collect very, very large amounts of energy through the atmosphere, through what you'd probably call radiation, cosmic radiation. But also, remember, when you're working with electrical collection devices, there is also the potential that lightning might strike it and other things might occur. And lightning in itself is very, very, very high voltages. So, you know, the millions of volts in any lightning strike. And they potentially can instantly kill a person if you're not careful with the way that you manage everything. Right? So, you know, on your house, most of your houses, well, pretty much all houses have to be in Australia, built with a earth strap that's put into the ground. The main reason why that is to stop the house becoming a charged entity that when you touch it, it electrocutes you. So, you know, in a lightning strike, for example, that is potentially able to occur if the house wasn't earthed in some way.
Does that earth mean that that energy is actually taken to the earth? Is that what that means?
Yeah, well, let's look at a few basic principles with regard to the flow of electricity, and then we'll understand some of these principles, right? If you think of where the house is sitting on the ground, from the water-based solution that we've just put in place, you could say that is 0 volts. You could also say that is the earth, or the area, or the what you would call the reference point, through which every other thing is measured. Does that make sense? So when you build a house, for example, where you place it becomes the reference point of your property to its fair degree. With your collection of water, if you collect water off of your house only, the only way to feed that water back into the home is to either wait until all the tanks are full, but even then the pressure isn't very high, is it? And it flows like a dribble. Or we need a pump, something that charges the line more into a higher pressure. Right? So if you think about it, if you don't have a pump, what would you do? Well, if you had a house built, what would you do? You'd gravity feed, yes? Right? To gravity feed, you need to put something that collects the water in a much higher location than your home. Is that not true? You could say that where that collection point is and where the house is the potential of how fast and how much pressure you're going to get in terms of how much water will flow. Can you see that? It's exactly the same principle in electronics. Exactly the same principle. If the tank was lower than the home, then unless you have, and there was water in the home, then the water in the home would flow back into the tank at the same pressure. If the tank was 10 metres lower than the home rather than 10 metres higher, the water would be flowing from the house into the tank at the pressure of whatever 10 metres is. Right? But if the tank is 10 metres higher than the home, then the water will flow from the tank, if there's water in there, to the home at whatever pressure 10 metres would allow. Can you see that? So in one way, the current of the water is flowing in that direction. If the tank was down here, then the current would flow in that direction of the water.
So if there's no energy devices, does the current flow is dependent on gravity itself because it's another form of energy?
No, do not confuse gravity with anything to do with electrical properties. What I'm doing is just making an analogy so that you can understand how electrical things work. Does that make sense? Yeah? Erin?
The question was about Earth though. So how it is actually when the electrons hit the Earth that their voltages become 0.
That's correct. All current flows the way, because the Earth is our only reference point for current flowing, Earth becomes a 0 voltage. The Earth itself becomes a 0
It
voltage.
always flows towards the Earth, doesn't it?
It can flow out of the Earth if our voltage is negative in comparison to the Earth. So it can flow in either direction. This is why I say it's a reference point. It's like putting your house at a certain point on your land. Anything that's above that point becomes a positive. and anything below that point becomes a negative. Does that make sense? And so this becomes, if you like, 0 volts, or Earth. Anything that we potentially can put below it. Now, obviously, you can't put anything below the Earth, although you could drill a hole into the Earth, drop something 20 metres in that hole, and now it's going to flow, the water, if it's water, it'll flow from your house into that hole. So that is potentially a negative, what's called a negative potential difference. Does that make sense? You're still confused.
Potential difference thing, I just am relating it to electrons, that's all. Like, if I have a positive charge right now, it's going to go to Earth, isn't it?
Yes.
Yeah, that's it.
And if you've got a negative charge, it will come from Earth.
Yeah.
But there will still be a flow.
Yeah.
So you don't think that if you've got a negative charge that there'll be no flow.
Yeah.
Right? Because a negative flow of current can kill you just as much as a positive flow of current can kill you.
And it's electrons then. Oops.
It's electrons flowing in a certain direction that is current, yes. Yeah. We'll talk about the electrical principles in a minute. The key is to start with something that you understand, and then we'll move into something that is a bit more difficult to understand.
So either way, if it's a lightning strike coming down of some other phenomenon that's coming up, it'll disperse across Earth?
That's correct, yeah. Earth, what happens with Earth, in practicality, what happens if there are very, very high voltages that are being discharged to Earth, then around where the discharge point occurs, there will often be a very high density of current, and then the current will flow out from that point. That's why sometimes when a lightning strikes a tree or something, the whole tree disintegrates, because at that instant, the tree becomes the conductor to Earth, and the density of the current causes the tree to sometimes even explode because of the amount of heat generated. So in practice, there is no such thing as an instantaneous 0 voltage in practice. In theory, there is, but in practice, the practice does actually very closely correlate to the theory. If you have a static, for example, if you generate static electricity in your own body, you might have 20,000 volts of charge, of potential difference between your body and the Earth. You touch the Earth, you're going to have that 20,000 volts instantly discharged. The reason why it makes a sound is because just before the point of touching, it discharges through the gap. The gap is like a high resistor, a big resistor, but once you have the point of discharge at a certain point, it'll now jump that gap. And as soon as it jumps that gap, it's now discharged the potential voltage.
It depends on the amount of energy that
Stored.
the gap too.
Yep.
Like a smaller energy, a smaller gap.
A small energy, for example, a 1.5 volt battery is not capable of jumping hardly any gap at all that's measurable. Right? A 12 volt battery, if you touch the two terminals together, which is quite a dangerous thing to do, because there is a potential of the battery itself exploding and you're getting lead and acid all over you. So I wouldn't recommend doing it. But if you did, you would see that you get closer and closer current, and it gets to a point where it can jump the gap. Even 12 volts can jump the gap. But if you imagine 20,000 volts, now that can jump quite a large gap. And the gap is, it has a square mathematical function to it. In other words, it takes the squared amount of energy to jump a gap that's double in size. So in other words, let's say a 1 millimetre gap could be jumped by 12 volts. Then to jump a 2 millimetre gap, we need 144 volts. Does that make sense? We need to have a huge amount of extra energy to jump those extra gaps. Yep.
Is there a potential, if there's too much or a lot of energy concentrated at one point that goes into the Earth, is there a potential for it to come out anywhere else besides staying in the Earth?
If the entry point to the Earth is well earthed, then there is no danger really of it going anywhere else very much. But you must understand that very, very high voltages, such as a lightning strike, contain very high voltages, and they have the potential to, in a certain range from that area, to actually cause a flow of current and therefore a potential difference across that range. So you can stand, let's say let's say a lightning strike happened here, and you could stand here, and you could probably you're still going to probably feel the effects of that strike because of what's happening on the Earth around you with the dissipation of the energy, right? But if you stood over here, 20 metres away, you'll hear it, see it, might be frightened about it, but it's high down lightly, it's going to actually hurt you.
That's why you keep your feet together when there's a lightning potential of a lightning strike.
Because if you keep it apart, there has a potential of flowing up your body and down the other side because of the gap between the two voltages that are on the ground in the flow of that energy. Right?
You get enough static on the trampoline, you can actually see the spark between
can,
the trampoline frame
Yeah.
and your finger.
Yeah. And with the trampoline, sometimes it gives you a bit of a kick, doesn't it? Like when you get off the trampoline and touch the metal on the outside, you get that kick. It's the same kind of principle.
So the Earth can't become a battery as such?
Not really, but there are some physics principles that you discover in advanced physics that you realise that the Earth in itself is a form of a battery. That things do flow from it and to it. So therefore, there are some advantages don't really need to raise at this point, but the Earth itself is capable of being a battery of some kind, yes. But we don't need to worry about that too much in the basics.
But when the 20,000 volts enters the Earth, where it goes? Because it's just another body too? No.
And yeah, the beauty of the Earth is that it dissipates the energy and usually as a result causes chemical reactions in the dissipation of energy. And this is why a good lightning storm has a beautiful effect on plants and other living things because it converts much of the energy that's electrical into chemical forms of energy over the surface of the Earth. And that then causes the you could call the regeneration of different elements inside the Earth itself. So the whole process is actually very, very beneficial to the Earth. But if we look at it from an electrical perspective, that basically Earth is zero. Anything that's below Earth, it's like digging a hole, and that is negative. And anything that's above Earth is positive. In terms of the flow of current, then we won't generally go astray as to what's really going on. Yes? Because the reality is, like, when the clouds rub together, they actually form a negative charge, not a positive one. And the reality is that a lightning strike comes from the Earth to the clouds, right? So, because the clouds are generating negative voltage or a negative potential difference between the Earth and the clouds. So the actual current is flowing from the Earth to the clouds to neutralise the clouds' voltage.
So what we see with the lightning strike is like we don't see the electrons, but as soon as the electrons get to the positive point, then all of a sudden we see the light.
You see, the flash happens instantly because the light travels at the speed of light. So from an observational perspective, you cannot see where the source of the flow of the electrical charge is coming from. The only times that you can actually see it, sometimes, and even then you only see it as a flash, is when you get a cloud-to-cloud lightning strike, where it goes from one cloud to another, and that happens because of the potential difference between those two cloud systems that are very highly charged in a different direction. So one might be at 0 volts and the other one might be at 1,000,000, and once the two clouds start coming into proximity, bang, the one that's at 0 volts supplies the current to the one that's at 1,000,000 negative volts. Does that make sense? And you get a lightning strike. But the lightning strike, when you observe it with your eyes, you can't tell actually whether it's coming from the Earth or to the Earth or from a cloud to a cloud because it's happening at once. Right? And that's the reason why is because anything that happens in terms of a discharge that we can observe with our eyes happens at the speed of light, which is very, very fast, 144, what is it? 144,000 kilometres per second or something like that, is it? 144?
3 by 10 to the 8.
3 by 10 to the 8, sorry. Yeah, 300 million kilometres a second or something like that. So we can't really see that. We can't measure that very easily with our eyes. So getting back to this, does everyone understand the difference? It's very much like a pressure system with regard to a watering system.
The voltage is the positive?
Is the potential difference. It could be positive or negative.
Okay.
Yep.
Oh, so it's not both of them added together?
Well, the difference between those two does create double the voltage, yes.
Yeah.
So if you had at the same time,
okay,
which is possible, one with a positive and one with a negative, so one's positive 10 and one's negative 10, then the difference between the two is 20. So the amount of current that will flow will be twice as much as if the difference was 10.
Okay, so it can be either?
Yes.
Is that what's created in AC? That's what I was trying to ask before. In AC current, or in alternating current, is that?
But we need to understand AC current a bit differently, because AC current has a waveform to it, and the reason why is because the two voltages do not exist at the same time in the same place. Does that make sense? Yeah. We'll talk about that in a minute.
And so it's like the watering system. The electrons only have power when they're in motion. Is that right?
That's correct.
As soon as
The power is there, you could call it, but it's potential energy at that point. Just like when you charge yourself up on the carpet, you are a walking bundle of potential energy. Does that make sense? It's only when you earth yourself on something or touch another person who's at a different voltage that that potential energy is transferred into actual energy that now has an action of some kind.
It's like soul, isn't it? Before we take action, it's all just potential. God put all this potential in us, and when we activate our desire, suddenly there's creation.
Yeah. Now the power is useful. Yeah, exactly the same principle. Yeah. Is there any other questions so far?
How do you get a negative charge?
It's very easy to get a negative charge. It's just as easy to get a negative charge as it is to get a positive charge. But we'll describe how charging occurs as we go along, right, rather than now. Huh? So, can we see what current is in terms of... Current is the flow of the water, isn't it? And it's how much of the water is flowing at a certain period of time. So it's how many electrons are flowing at a certain period of time in electrical principles. Voltage, can you see voltage is the potential between, you liken it to the potential between where something is and where it can flow to. The potential between those two places is called a potential difference. And quite often in electrical principles, we use the term potential difference rather than voltage. Does that make sense? Because the reason why is that let's say you've got a plus 12 volt there, and then there's 0, and then there's minus 12 volts. That is a voltage called plus 12 volts. That is a voltage called minus 12 volts. But if we connect those two up together with a resistor of some kind, the potential is actually 24 volts. Can you see? So we often refer to the difference between voltages rather than the actual voltage itself. And the difference between the voltages is this potential difference, where something can flow from and to. Does that make sense to everyone? Yep. You can see that you could say, oh, it's not very good. You can see that I could say, I'm standing here on 0 volts on the earth, I'm fine. And that's not strictly true. Because you could have a cloud system above you at minus 1,000,000 volts. Does that make sense? And the potential difference between the earth at 0 volts and the minus 1,000,000 volts up there, and it might be tens of millions or 20 million volts or whatever, and if I'm at the highest point, in between those two places, I am not very safe at all. Right? So this is why in a lightning storm, if you have a lot of storm and you're on top of the hill, it's a good idea to go down from the top of the hill and maybe lay down on the ground. So does everyone understand that voltage in electrical principles is like the potential difference of where the water is stored and where it can flow to if you put a pipe in? And the resistance, this resistor, is all about how big the pipe is. If it's a very, very, very tiny pipe, then it's higher resistance and therefore less flow of water or less current will occur for the same voltage. If it's a very, very big pipe, there's hardly any resistance at all, lots of the water will come out all of a sudden. Yeah? So it's like getting a bucket of water and just throwing it over somebody. There's not, whereas the first one, with the higher resistance, is like getting a bucket of water and pouring it down a 4mm tube, which will take a long time. Yeah? See the difference?
In your drawing, the positive bond would be the house of the earth and the negative the water tank?
In this case?
Yeah.
No, if you could just think of it, all I'm trying to do is describe some basic principles here. And the flow of water is very similar to the flow of current. And what I'm trying to illustrate to you is that all we need is a difference in the height of the water for flow to occur. So for flow to occur in electrical principles, all we need is a difference in the voltage or the potential between two voltages in order for current to flow. It's the same principle. Don't get too hung up on what's comparable to what. Don't take the analogy too far. Does that make sense? Is there any other questions before we proceed? Now, what I would like to do is sort of draw that similar thing for you, because the drawing of that is a bit different if we look at it from a perspective of electrical principle. We have different symbols that we use to indicate different things. So, for example, that symbol there is the symbol that we use for a battery. Or you could call it a voltage source, but it's a DC voltage source. In other words, it's only in one direction. Does that make sense? Now, that's the symbol we have. If you can think of that, that's similar to saying the tank is 10 metres above the house. So if this was a 10-volt battery, let's think of it like, right, that means the tank's 10 metres above the house. If this was a battery source, like when the clouds rub together, for example, the battery, the cloud becomes like a battery that's 20 million volts or higher, a huge amount of voltage. Does that make sense? It's still a battery though. It still is providing a direct current voltage source. Everyone's okay with that? Mary?
Sorry. So does that mean that really a battery, if I'm thinking of the cloud, or now I'm thinking of a battery in relation to the cloud, the battery is only ever creating
a potential for something for current to flow. To complete the current flowing, we need a circuit. We need to join things together and then it will flow. But understand, in some cases, the air can be a circuit.
Yes,
like in the case of a lightning strike. The air itself is a circuit. Right? So you've got to be very careful working with electricity. Just because you haven't got two wires connected together, it doesn't mean that you can't be hurt. Does that make sense? Yeah?
That way sometimes too, lightning strikes, they shoot out rather than just one going straight down.
Many of them shoot out because they are discharging in lower voltage regions in the atmosphere. Yep. And so there is a flow of electrical energy, electrons from the lower voltage from the the lower voltages to the higher negative voltages. And so we get that branching out effect occurring. Yeah?
Two people, they can create an energy, right?
Yes?
And then when that energy, like you touch something,
Yeah.
their energy goes through.
That's right.
Is that right?
Yeah.
And what does that actually...
So when you're generating what you call static, right, you are actually becoming a battery. You are becoming the battery. You are a higher voltage source than the earth that's around you, and you're insulated from that source. So you are now the battery. Right? When you put your finger near an earth source, right, there'll be a certain amount of gap needed before the circuit is closed from that energy's perspective. And as soon as that gap is closed enough, the circuit completes and bang, you get a discharge of that energy. Right? An electrical current flows, in other words. Yeah?
So if you had 10 people holding hands, rubbing their feet on the ground, one person touch something and multiply it greatly or not really?
Potentially, but it just depends on the positive and negative amount of energy and where it's stored in the body as to where the current will flow. So if I hold onto your hand and we both generate electricity, as long as you at your end is higher than my arm and my arm on that end is higher than this arm, then the energy is all going to flow in one direction. Right? But we could be both doing this and the energy from both ends being opposite and they flow in and cancel each other. It just depends on how the voltages are actually aligned with each other. Does that make sense? Yeah. No, but these are all important questions because when we're collecting energy from the atmosphere, we need to understand that the air itself can be a conductor of this energy. So we might be near one of our collection devices and get electrocuted without even touching it. So we need to be very careful as to we need to understand it. Does that make sense?
Yeah. I'm just wondering why, a simple question, why electricity hurts. Like why when you put static against two people then it gives you a sting. What's going on there?
Well, there's a lot of reasons why it hurts. Firstly, your body, so your heart itself, is controlled by electrical impulses, and so when the energy flows through you at a certain level of current, there is the potential of it interfering with the heart's beat, which automatically generally creates a fear-based response in a person, which then has a physical response. Secondly, one of the other reasons why it hurts is because it generates huge amounts of heat generally as well, particularly high voltages like for instance lightning generate huge amounts of heat. So your actual flesh can burn from the electrical energy flowing across your body. So there are a number of different ways in which the energy can hurt you, if you like. So the energy that's dangerous from our perspective is the energy that is strong enough to burn us, or the energy that is strong enough to stop our heart. Yeah.
And how many volts might that be approximately?
It doesn't have to be a very high voltage. There's a certain current range generally that the energy can stop our heart, and it has to be a certain type of current as well generally. But direct current and alternating current can both stop your heart. Direct current can also start your heart.
So that's the shock thing.
That's when they give you the paddles, right? If one paddle is a positive and one paddle is negative, they put them in different places on your body and bang, the electrical charge goes through there and it can get the heart started again. So don't view electricity as something you always have to be afraid of. It can actually help us as well. Right? So it's not something that you need to be afraid of, you just need to understand it.
How can we measure it?
And there are measuring devices that measure current, voltage and resistance and other things. And next time I come, I'll bring you along some of those devices and show you how to use some of those devices. Some of them are very cheap devices, and I'll be leaving with the team, I'll be leaving a quite cheap device with you, but I also have some quite expensive devices. And in terms of measuring alternating current, there is a way to measure alternating current that without seeing it, or you can actually nowadays measure it by seeing it on a tracing screen, which is called an oscilloscope. And you can actually measure and watch the current. But those devices, particularly at the frequencies that we'll be looking at, and we'll talk about frequency as well in a minute, at the frequencies of alternating current, the frequencies we'll be looking at are probably going to be very, very high frequencies, and they've yet to really make devices that can measure those frequencies without spending like in the hundreds of thousands of dollar ranges for the equipment.
With respect to the electric shock, time plays an effect too. The longer the shock, the more dangerous it is.
Of course. So if you just briefly touch something, that might have a certain effect, but if you hold on to it, obviously that's going to have a completely different effect. And there is also problems with alternating current. If you grab hold of something that has alternating current, your body goes into this convulsion type of process, which means that you can't pull yourself away from it very easily. Whereas with direct current, generally when you touch it, you bang, there's sort of like a static electricity discharge with direct current. So even the type of voltage is going to determine how much you get hurt from it.
Because it activates your muscles.
Exactly, it starts triggering your responses in your muscles, the electrical responses in your muscles, which are all to do with how your muscles interact. So it's important. The two types of current, direct current or alternating current, we'll describe them in a bit more detail in a minute. Both of those two types of current can hurt you, but usually alternating current is the current that kills most people.
My high school physics teacher said, if you really want to touch a wire to see if it's electrified, do it with the back of your hand so that your muscles don't contract, so that you can't.
Yeah. Why you would touch a wire to see if it's electrified, I don't know. Do you know what I mean? Like, it's sort of like, oh, I can touch that and see if it's electrified, but gee, if you've got a multimeter.
It is a good technique if you've got to touch the wire anyway.
If you've got to touch the wire anyway, and you've turned off the power to your house and you've made sure everything's and you reckon you've done everything possible, still don't go and grab it with your hand like that. Touch it first like that, with the back of your hand, and then if you get no response from that, then you can figure it out and do something with it. Does that make sense? But make sure you do all the safety things first. And can I point out too that the old televisions have cathode ray tubes, right? The cathode ray tubes usually operate anywhere from 20 to 40,000 volts inside of them, and they act like what's called a capacitor. So what happens is, if you turn off the power, they store that 20 to 40,000 volts permanently for a long period of time with a very slow discharge rate. So you could actually go up to a telly that's been turned off 2 weeks ago, start opening the back of the telly up and get electrocuted, even though it's not connected to any power source. Right?
Can you like put a capacitor really high up on the hill and then if it got struck by lightning and hold some of the energy?
Theoretically, yes.
Or it's just like...
Well, theoretically that's possible, but they haven't yet made a capacitor that's able to do that. But theoretically it is possible. Yeah. We'll talk about capacitors in a minute.
You know how I said when you have friction and then you touch something, or why does there a light occur? What's actually, why does that energy become light?
Anytime electrons pass a gap, they will or flow, they will always produce heat. The reason why it produces light when it's passing a gap rather than in a copper cable is because in a copper cable it produces heat before it produces light. Right? Across a gap it produces heat instantly, and it's a very, very pinpoint amount of heat, so therefore you can actually see the flow of those electrons. Whereas in a copper pipe or a copper piece of copper wiring, you can't actually see the flow of electrons very easily unless the flow of electrons is so intense that the copper itself starts melting. And that is possible. the flow of electrons does cause heat in every case, and so it is possible to melt a wire. Some of you might have even done that when you put the wire across a battery or something like that, and if there's no resistance, you'll heat up the wire so much it will just melt, and how thin the wire is will depend on how fast it melts.
So that, if I go back to your analogy of the tanks and the house and the pipes, does that mean that if I have a high current with a lot of resistance, I might melt the wire, like busting the pipe?
Yeah, it's a high voltage. So if you have pressure, and if you just imagine if you had intense pressure and you had a very thin membrane pipe, and you had intense pressure, the pipe is trying to restrict the flow of the water, but the pressure is trying to force more water down the pipe than the pipe's own physical membrane can handle. And you get a pipe burst as a result of that. Well, it's exactly the same with any electrical circuit, and including air, is that when you get the bursting principle, you firstly usually get a lot of heat generated and therefore a lot of light generated, and the wire itself can disintegrate.
So is that why, say I'm using the blender, very pragmatic, using the blender and it's stuck, so it's not
turning, but it's still getting the same amount of voltage pumped through it.
I can blow up the blender.
You can blow up the blender. Yeah. And in fact, many people do not know how to use household items, particularly motors, and they often ruin the motors by their usage of the motor by putting too much resistance on the motor's ability to turn. And when you pass the same amount of current through something that you're resisting its turn of, it generates heat because there's no discharge of energy into another form of energy, like magnetic energy, and so it discharges heat instead and melts all the internal windings of the motor, and then you've got a useless motor that doesn't work at all, with a very strong burning smell. It's actually very dangerous too, because it obviously can actually even melt to such a point that some of that wire touches the casing of the device, which means then the casing of the device is now electrified, and potentially you can even hurt yourself. Okay, is there any other questions at this point? Mary?
This is what I was like in high school too. So when you're talking about, with Lauline's question about jumping the gap and you get light, is this the first light bulb? It was jumping the gap?
The first light bulb is a similar sort of principle, but it's a winding, a filament, that is made to burn. And you pass a certain amount of voltage across it, which means a certain amount of current flows through it, and the current produces light and heat, and therefore you get a lighted effect from that particular element, and they pass just enough through it so that it doesn't disintegrate, right? And they usually pass less than that. But there are some elements that we have, some electrical, chemical elements that we have that enable the passing through of electrical energy without disintegrating until they get to but still producing light until they get to a certain lifetime. And that's why a bulb eventually does break.
So like these fluoro tubes, you're saying how air can conduct electricity, they've got a gas that conducts electricity.
That's correct. Yeah, it's a gas that conducts electricity in a fluoro tube. You've got a positive and a negative, and in fact it's alternating current across the tube generally. Although with these they rectify, with a fluoro tube they rectify it, I think they do, to high DC voltage, and the DC voltage is between the positive and negative of the tube, and it lights up the gas. The flow of the electricity between the two lights up the gas, and the light is being produced from that. But the gas is like a wire. You can think of it as like a wire. It allows the flow of current between one polarity of the tube and the other polarity of the tube, the other connectors of the tube.
And is it true that people have discovered all this about electricity, but they don't really understand it?
That is true. Mankind still does not understand electrons, the nucleus of an atom, or or any of the other things. They have only got theories associated with it. And what I'm describing to you really is what you would call the theory that is universally accepted about the flow of energy. And nobody has proven the theory to be wrong after hundreds of years now of investigation. And so these theories are retained as a fact until such a time as somebody proves them to be wrong.
And so this is like our framework for further exploration.
Exactly. It's our framework for further investigation. The reality is that we'll be involved in further investigation that hasn't been heard on the planet at this point. But you need to know some basic underlying principles so that you don't die in the process. I like that. Well, obviously there are some forms of investigation that are potentially dangerous, and as long as you understand what's going on, then you'll have a high degree of safety. If you don't understand what's going on, then there's a chance that you can harm yourself in your own investigation for the truth, and that's pretty pointless to do that. Yeah.
I'm just trying to see, not bring the water as a comparison, but you have different types of energy that's formed by hydroelectric. So that's a lot of water doing something and creating electricity. How does that happen?
Well, it's very simple actually. If you imagine our tank, which is like a dam with water in it, and you've got a pipe that the water flows through, if we can put some kind of device that catches that water and turns a device, we can turn this flow of water into electrical energy. Right? It's just some kind of device here, we'll describe the kind of device later, that you can turn around, and in the process of turning it around, it produces a different type of energy from this flow of water. And that's how hydroelectricity works. It's very, very simple. Very simple. That's why it's very easy to create.
Yeah, you probably think of it as a little propeller.
It's not so much it's a little propeller catching the water, but turning a shaft that is connected to a motor or an alternator, and this alternator generates charge. It generates electricity from the motor turning. And the motor has a combination of magnets in it and wires, and we'll talk about the interrelationship later, because there's a lot of things we need to understand before then, but there is an interrelationship between wires and magnetism and what you can do with those things to form electricity. Right? So it's just like a little propeller that catches the water and spins a rotor, and the rotor is connected to a motor of some kind, let's just call it that at the moment, and the motor is a combination of magnets and wires. And in the process of it turning, it forms energy. It forms electrical energy, which then can be transmitted. Yeah? So I don't know if you've ever visited a hydroelectric scheme, but they have these great big motors, if you like, if you want to call them that, usually sitting, in very stable environment, very connected, because they're producing huge amounts of energy, and they're spinning at quite rapid speeds, so they need to be made with quite a lot of precision. And they're quite large. There are some that are as large as this half of this room, one motor, producing electricity.
Is that the same as the wave electricity?
It's the same principle. Anything that flows that has energy in it can be turned into any other form of energy. That's the beauty of all of this. We can turn one type of energy into another type of energy. Does that make sense to everyone? And what we're doing electrically on the planet is we're getting potential energy, heat or water flow are the two primary ones we're currently using, or atomic reactions is the third one that we're currently using on the planet most of the time. So when I say heat, there's coal-fired stations which produce heat, produce steam that drive turbines, and the turbines produce electricity. With regard to a radioactive, a nuclear power station, you've got the nuclear rods in a process of radioactive decay, produces heat, that heats up water. The water then is used, produces steam and has enough energy to turn turbines that then produce electrical energy. Or you have hydroelectric scheme, where you've got water flowing down a pipe that due to the difference in height, it's a lot of water coming down the pipe with a lot of force behind it, and a lot of times the pipes are quite large, a lot of force behind it. They drive motors that produce energy. So you can convert all forms of energy, radioactive energy, you can convert water-based energy, or you can convert heat to electrical energy. Does that make sense? Any of them.
I'm just wondering about the lightning again. You know, in the city how the tall buildings often have a lightning thing on the top of it.
Mm-hmm.
Is this so that the whole building doesn't become active in the case of a lightning strike?
Yeah, imagine if you had a tall building and there's clouds up here with it's actually a negative charge, right? That's millions of volts. The cloud system goes over the top. That happens to be the tallest building. Where is it going to hit? It's going to hit the tallest building for sure. Does that make sense? Because that's the one that has the least amount of gap. So unless it can jump that gap, it's not going to jump that gap. But as soon as it gets this one, it's going to jump that gap for sure. So it's going to jump. It's going to hit this building quite regularly, the lightning. So what they do is they put an earth spike with an earth strap down to ground that runs alongside the outside generally of the building, or down some kind of conduit in the building. And that then means that all of that energy is dissipated down there instead of flowing around the actual building and potentially electrocuting people inside the building.
With the bit that goes in the earth, so this is the same as what you said that all houses have too?
It's the same, but much bigger.
How deep does it go and what is it?
Well, it depends on what type of earth and how much water is in the earth and what kind of earth it is, whether it's clay or sand, or, you know, there's a lot of variable factors as to the resistance of the ground. And so, but a lot of times what they do is they suggest to bury it, you know, up to a metre deep generally if it's a house, with enough current, enough thickness to have large amounts of current flow through it without melting it. And that way it's got a lot of area that it can dissipate through. But it just depends on the type of soil as to how conductive it is.
And is it like a big metal thing, or what is it?
Yes, it's usually a highly conductive metal that's actually dug into the ground. Yep.
Sometimes they connect it to the water pipes because the water pipes are metal that run through the ground.
Exactly. The beauty of connecting it to a metal water pipe is the metal water pipe might run over kilometres of time, and usually the thickness of the pipe is very high, so therefore it can carry very high amounts of current. And because it's dissipated over a system, if you can connect it to the water pipe, you can, and it's a copper pipe or that's buried under the ground, then you'll dissipate the energy very rapidly. Does that make sense?
Yeah, they stopped using that practice after a while because there's airfish leaks in the house and people getting tingles off the taps.
Exactly. Yeah. So just to, yeah, but they used to do that a lot, like before, yeah. But nowadays they try and do it so that each house is isolated.
If that's an earthing system where it goes to the earth, what is it when you have in a wire when you're doing the plug, but a green one, a yellow one, an earth one? Where does that go?
The earth one goes to earth.
Through you? Or?
No, it's a connection. We'll talk about the way that AC is wired in a minute, but which is different to the way DC is wired. DC, you only need 2 connectors. AC, you can get away with 2, but you're far better off with 3 connectors, and we'll talk about why. Yeah.
So when you have your appliances and you plug it into the power point,
Yep.
like how the bottom one is called earth,
Yep.
so that somehow is connecting to this system in the house?
That's connecting to earth. Yep. It
So
should
the
be.
wiring would somehow connect to this thing in the ground of your house?
Yes, it should be connected to that in the ground of your house, yes. And then you can get what's called an earth leakage device, and that tells you when something's leaking current to earth, and that can switch off the power of your house. So that's a very safe way of managing alternating current.
Why? I don't understand that. Why is it a problem if something's leaking current to earth?
Because it means it's charged without you having the switch turned on.
Alright, if you're not running
which
it.
means
so,
there's some problem with your wiring
Okay.
in your home or the wiring of the particular device you're using. We'll talk about some of those principles later though. We need to understand the basics. So far we're right with the questions? And I can continue with some of the basics? Okay, well I'm going to go to the blue first because I need to eat. So maybe if we just have a 5-minute break and do the same